Let me introduce Dr. Zhou,
Thank you.
who is Associate Professor at SUNY Poly. Sorry. He's going to give a talk today on intelligent control approach for maintaining wireless communication connections in multi-robot systems. And I don't know if you know that you has been the leader for our first, which league is it?
First
FRC. No.
Not the leader. I mean,
Yes,
just
you
a
are.
mentor. Just a mentor.
He's been our faculty mentor
Yeah,
for
just a
students in the Lego League, the highest level of the Lego League.
Yeah, let's see, that's
FRC.
not Lego, that's real robot, whatever.
Yeah, dealing with-
Metal robot.
So you're not only teaching this and doing research in this area, but you're actually been mentoring students as well, which we
Yeah.
appreciate. So we're looking forward to your talk.
Well, thank you very much, Deb, for your nice introduction. Actually, we know everyone here, so that's fine. It's first time to know Marv. Nice to meet you. Well, so as you know, I'm a mechanical engineering guy, so my research area is robotics. And there are many aspects. Mobile robots and multi-robot system consisting of mobile robots is one important aspect of my research in robotics. And today I just talk about a specific ongoing research problem, intelligent motion control for maintaining wireless communication connections in multi-robot systems. And in today's talk, you may see less mechanical engineering flavor. Probably John may ask, why do you steal our computer science idea? Okay, I just try not to isolate myself from other disciplines. Anyway, robotics itself is an interdisciplinary research field. So it is very common to collect all kind of approach originally developed in different fields to use them on robots. Okay. First, I want to talk a little bit about the motivation of this research work. Here, we focus on multi-robot systems consisting of multiple mobile robots collaborating to execute tasks. You see those pictures, those are different examples of multi-robot systems, from swarm robot to robot soccer team to mobile manipulators carrying one thing together. And there is on the bottom, there is a team of mobile robots mimic the Mars exploration scenario. Then on the lower left side, we have two UAVs, two teams of UAVs. And each of these robots has onboard sensing, actuation, wireless communication, and computation capability. Okay, and these multi-robot systems, they have potentially numerous applications. From civilian tasks like surveillance, environmental monitoring, disaster rescue, transport. You see some of the examples here. And to scientific activities like space exploration, deep sea exploration, as well as military operations like demining, battlefield scouting. So those are commonly listed examples for multi-robot application. Well, compared to independent individual robots, those multi-robot systems, they potentially have a higher flexibility, efficiency, and reliability. They can accomplish a single task much faster than a single robot. They can execute a task beyond the capability of a single robot. And a team of non-homogeneous robots, they can handle a variety of tasks. Okay, and a team of robots, they can provide a parallel mobile sensing and computation. Moreover, a team of robots is less influenced by the failure of individual robot, so that's more robust. One important observation is the performance gain of a multi-robot system over a team of independent robots really relies on the coordination among the robots. And the coordination among the robots rely on communication. So that's the reason why we work on the communication. Okay. So by saying that multi-robot communication maintenance is a fundamental problem for multi-robot system. In fact, many multi-robot system application requires to deploy a team of robots into an unknown environment to form and maintain some kind of a communication coverage to support system management, data transfer, task coordination, all those kind of things. However, in physical environments, in real environments, it is quite challenging to maintain wireless communication connections among the robots. The reason is that in such environment, the distance, obstacles, robot motion, and other environmental factors cause signal decay, reflection, diffraction, scattering, shadowing, fading, and resulting not only limited but also unstable communication range. So that's the trouble. Therefore, we want to deal with that, deal with this fundamental research problem. People use different ways to handle it. People use different ways to handle it. Well, in my view, I consider the bunch of approach handling wireless communication maintenance among robots belong to two categories. One is a pure communication based method, based approach, basically to control the communication channel, to maintain, to reconnect communication. Okay. Another category is what I'm belonging to. Basically, that's the robot mobility control approaches. So to control the robot motion, to let the robot move, to adapt to fluctuating wireless communication connection. Okay. So since I'm a mechanical robotics guy, so I just work on this side. I really don't have as much knowledge as John on wireless communication. Okay, so yeah, I can only claim on the motion control side. Then by saying the motion control for multi-robot communication, it really requires that because of the unstable communication condition in the real environment, it really requires very quick adaptation of the robot position to the wireless communication connection. Okay, and generally speaking, the control approaches for robot motion control, for multi-robot motion control, can also be categorized into two categories. Okay, centralized control and distributed control. The centralized control requires one leader, collect all the information from all the robots, make a decision for all the robots, and send a command to all the robots. Okay, it works pretty nice in stable environment, stable system, in slow tasks. However, it has a lot of drawback. It relies on establishing the network, which doesn't work clearly. For this reason, we cannot use this method to do the wireless communication maintenance in multi-robot. Also, it requires high communication complex, it results in high communication complexity. It has slow response to the changes in the system and the environment. It requires high processing power for the leader. It is vulnerable to the failure of the leader. If the leader fails, the whole team fails. That's it. Okay. Then on the other side, the distributed control, right? Each robot behaves according to local information. Then the combination of all robots' behavior achieve the global goal. This allows each robot to self-control, which is very nice. Therefore, it is adaptive to the changes in the environment and system. And it is highly scalable to large multi-robot system. Okay, and we consider this category of control. This category of control approach, they are suitable for unknown environment and dynamic applications. This is basically what we want. So we focus our research work on this category. Okay, there are some existing approaches on my side, on the motion control side, as I know, to deal with the maintenance of inter-robot communication. Okay, but existing approach mostly maintain the communication connections among the robots based on estimated communication range. And they also assume inside the communication range, the connection is stable, which is not true in physical environment. It's always fluctuating, unstable. So this lack of considering the uncertainty in the channel, in the communication channel, may lead to communication failure and further degrade the reliability of multi-robot coordination. So many of those methods only work on paper in simulated environment, not in the real environments. Then some other people also proposed to use a pre-constructed signal strength map to guide the robot in a known environment. that works to some extent. However, the map is not always available. If you have an unknown environment, how can you have a pre-constructed map like that? Okay, and also in situ, the communication condition always change due to all kinds of environmental factors. Always change. So it may deviate from the pre-constructed map. Then recently we see some reactive communication maintenance approach based on the online measured wireless link quality. This is something very promising, and we are basically pursuing in this direction. The problem with the existing method in this category is mostly work for only small groups. All we see is just 2, 3, less than 5 robots, something like that. Or they just work in the simulated environment. They got approved in the real environment. That's a problem. So there is a lack of robust solution to maintain connections with multiple neighbors with large team in realistic environment. Yes.
So I have a question. On the last one, that's clearly the one to pursue in my mind.
Yeah. There's something we also pursue in this direction.
Constantly monitoring signal strength, for example.
Yes.
It seems to me an issue there would be to balance the need for connectivity with the need for performing the task. And performing the task may also depend upon position.
Yes.
Is that part of
this is something.
There's a trade-off, right?
Yeah. That's an excellent question. I mean, in this work, we just work on the communication side.
Okay.
Yeah, we don't worry about the task.
So we're not worried about.
Yeah, but that has to be integrated into a more general control framework to take care of tasks. The good thing is that we don't need to maintain a specific value of connection. We just need to enter a certain range.
Yeah.
That's good enough. So that gives us some flexibility. Also, you talk about the robot position problem. Really, when you do a task coordination in a big multi-robot system, you have to consider all kinds of things. The robot position, the communication condition, system-wide. Then you basically allocate suitable robots to do one job. So there's also a task allocation problem in the global scale. So at this moment, this work is very big and it's very narrowed down to the local. Because putting into a general task coordination framework is going to be really big, very.
Depends on the task.
Yeah. It has to be a general task allocation algorithm, which can handle all those kind of complexity.
So, for example, the task may require that the robots be spread out.
Exactly.
And if you program each robot to go to the point of the best communications, then they're all going to go to the same spot.
Exactly.
And not be able to perform the task.
Yeah, exactly. Actually, there are some work we are doing in the same big project, but we haven't got presentable results yet. Yeah.
It seems that dispersing in space would be one of the basic requirements for almost any task.
Yeah, that's a basic deployment problem. Yeah, deployment problem.
So basically, you're getting them to cooperate with each other. Is that
Exactly.
the sense here?
Yeah.
That's pretty interesting.
Yeah.
Edmund was.
Oh yes.
If you lose a robot, meaning it becomes disconnected from the group communication-wise, is it lost or are there attempts algorithms?
Well, it depends on how you claim it's lost. If this robot is totally break down?
No. Mechanically it's fine, but the communication failed with all the rest of the team members.
Yeah, if so, then we have to do the reconnection. And the reconnection will use a different method from what I'm
So you'll try to reconnect. Okay.
Yeah, then the reconnection, mostly you will involve some kind of search exploration process to somehow pick whatever signal available in the environment and then trace back to the source, try to reconnect it. Yeah. That's another challenging problem. That's actually more challenging, tricky. Yeah.
Because in that balance, I would imagine that that has to be the prevailing thing, that you somehow keep the group. I mean, if you start losing robots left and right, you're going to be dead.
Yeah, that's true. That is true.
You may also lose clusters. You may end up with
Yeah,
disconnected
yeah.
clusters.
Same. But we try to maintain all the clusters somehow with a basic connection.
Yeah.
At least there is a
Yeah.
one connection between neighboring clusters. This is what we try to do. Actually, this method over here can do this. But if the connection is totally lost and need to do a reconnection, you have to do some kind of signal search. That I mentioned. Yeah. Okay. Well, so in order to solve that problem, so right now, let me see, make it more specific. So the approach here is mainly for the maintenance of communication connection. So you have some initial connections already. Maybe not perfect, maybe weak, maybe too strong, something like that. How to let the connection approach to the desired level, how to maintain the desired level. So that's this presentation about. Okay, so in order to solve that problem, and we also saw some, so like at the end of last slide, we saw some reactive communication maintenance approach. Then we wish to come up with something better. Also, reactive communication maintenance, but we want something better and distributed. So we wish our method can take advantage of robot motion to adapt to real-time fluctuation of the wireless link quality. And our approach should only depend on local information, should be a distributed control approach. And also, clearly, it should support distributed multi-robot task performance. Okay. Down to the bottom, we set our control objective like this. Each robot approach its neighbors, approach and maintains the desired wireless link quality with its neighbors. Okay. Then the combination of all the robots' behavior leads to the desired system-wide communication connectivity. Okay. So in that way. In order to achieve that goal, we look at some the category of intelligent control schemes for dynamic and uncertain situations. Specifically, we look at fuzzy inference, artificial neural network, and learning. Fuzzy inference, because it is adaptive to the uncertainty of input. In our case, the input is what? Wireless link quality. And there is some uncertainty, fluctuating. And artificial neural network, it is adaptive to no undefined relationship between the input and output. In our case, how to control the robot motion according to the wireless link quality. Wireless link quality is the input. Control decision is the output. Okay. Then learning. Some kind of a learning method can help us to train the controller to make it adaptive to in situ wireless communication situation. So combine all these things together, we come up with this approach, distributed fuzzy neural network control. So it's kind of a natural result, right? So you need a fuzzy, you need a neural network. So put together fuzzy neural network. Okay, so so give a little overview of our fuzzy neural network control approach over here. So a fuzzy neural network is a hybrid system combines fuzzy logic and the neural network. The control process follows fuzzy logic, which maps sensory input to control outputs through a bunch of membership functions and fuzzy rules. Then the controller structure follows neural network. And where the parameters of the fuzzy inference are tuned through the learning process of neural network. So it's a pretty good combination over here. Then the general control scheme of our approach is each robot is controlled by a local onboard fuzzy neural network controller. Okay, and each controller makes decisions based on a set of fuzzy rules, and each fuzzy rule is defined for the robot to map the wireless link quality with the neighbor to the communication maintaining movement with respect to this neighbor. Okay, and the control decision on how the robot should move relative to all the neighbors, if there are multiple neighbors. How the robot should move relative to all the neighbors. This decision is made by aggregating the outcomes of all the fuzzy rules for all the neighbors. Okay. And as a result, the establishment and maintenance of system-wide communication connectivity results from the combined control effect of all the robots. So two important things, I want to mention them before I go into the details. These are highly relevant to the control process. Number one is the sensory feedback. So we do the feedback control. We need sensory feedback. The sensory feedback is the measurement of wireless link quality, in-situ wireless link quality. There are several, many actually, metrics for wireless link quality. For example, the receiver signal strength indication, signal to inference, interference plus noise ratio, then packet delivery ratio, bit error rate, link quality indicator. And in our experiment, we specifically use this RSSI, receiver signal strength indication, because that's a popular measure of wireless link quality. It's available for Wi-Fi, for Zigbee protocols. In our case, we use Zigbee in our experiment. And this value is readily available. Just get it from the receiver so that we can use that for control purpose. And another important factor is the definition of the neighborhood of a robot. It's instantaneous because the robots are dynamic, they move around. So this concept is related to distributed control. So it's like a marching band. If a marching band wants to maintain the parade formation, so each person just maintain the space with the neighbors, with the immediate neighbors. So similarly, use this concept to a multi-robot system. For a whole system to coordinate, each robot only needs to coordinate with its immediate neighbors, right? Then the neighborhood is instantaneous. At each moment, we define the neighborhood of a robot as a set of one-hop instantaneous topologic neighbors. And specifically, we use the Delaunay triangulation to define the topology. There are some distributed algorithms to define the Delaunay triangulation.
So the assumption is that you can tell who are the nearest neighbors using the signal strength. Strongest signal is nearest.
Not necessarily based on the. Let me see.
Is that correct? Because even determining who's nearest may not be obvious.
There are two ways. Yeah. One, you can make the judgment based on the receiver signal strength. This is the one way, as you mentioned. Right. Another way is really when the robots can communicate with each other. Each robot knows its own position.
Sending coordinates.
Yeah, sending coordinates. Okay. That's a simple communication.
Makes it easier.
Yeah, that makes things a lot easier, actually.
So you have GPS, you're assuming GPS coordinates?
Well, in outdoor environments, you can use GPS.
Okay.
In indoor environments, we do experiment in indoor environments. So later on, I will show you, we use a visual landmark system to do the robot localization.
Okay.
Yeah. By saying that, the other day I saw your class. Your students holding a laptop in the hallway. Are they doing localization or something like that?
No, just measuring signal strength, RSSI.
Okay.
Yeah.
I was thinking that if your student can just locate themselves based on the signal strength, I can use that technique on my robot. But my robot needs certainly high positioning accuracy.
Yeah.
Right now we have a positioning accuracy in the probably 5 centimeters level. So
with visual?
Pretty accurate.
Can you measure Distance from time delay and location.
From what?
Time delay.
From time delay.
Yeah.
But that precision,
It's no precision.
yeah, it's very tricky because you see the wireless signal fly at light speed. So any little error,
Yeah.
you can see the ranging error. Then after that, you have to do the triangulation, trilateration. So the error is enlarged actually.
For small distances.
Yeah.
Yeah.
So we are talking about like for indoor application, we really talk about like a centimeter level, or at most a 10 centimeter level error. For outdoor, you can talk about a couple meters. So for outdoor, GPS is enough. But yeah, anyway. So okay, now let's get into a little bit detail of our controller. So first, the control process. As I mentioned, control process follows the fuzzy inference. So first, we define the input space. Input space is the range of all possible values for the wireless link quality. Then on the input space, we define 5 fuzzy sets corresponding to division of wireless link quality level. Okay, and fuzzy sets, they are called losing, weak, desired, strong, and crowding wireless link quality. Each fuzzy set is a set without a clearly defined boundary and can contain members with only a partial degree of membership. In fact, if you look at this diagram over here, the horizontal axis is a normalized input space, And on this input space, we define 5 fuzzy sets. They are overlapped. Therefore, for example, if there is a point over here, it can belong to this fuzzy set. It can also belong to the next fuzzy set. Okay, that's the meaning of fuzzy. That's the meaning of fuzzy.
So the horizontal axis is
that's the
decibel
input space.
signal strength or something.
Yeah, that's the input space, the signal strength space. Then, okay. So the 5 fuzzy sets, specifically, they are like these. The desired wireless link quality is the desired link quality level. So we try to approach and maintain that. Okay, the losing wireless link quality means the quality is really poor. If you get lower, then link is lost, disconnect. And crowding wireless link quality means that the link quality is incredibly good. That's probably all the robots are just crowded together. That's not good. The robot can do nothing. Okay, so in between, we also have 2 transitional level of wireless link quality: the weak and the strong. Membership functions, and each membership function maps each point in the input space to a membership value in the fuzzy set. So it is similar. It is similar to the probability function of a point belonging to a set. It's just in this case, a point may belong to one set, may belong to another set. So what's the probability? Not exactly same, but I try to find the similarity. I myself try to understand what's the concept behind this fuzzy. Okay. And for the membership function, we just take the simple shape, the trapezoid shaped membership function. You can see these are trapezoid shaped membership function. The reason for that is, they provided an effective but very simple description of the fuzziness of the wireless link quality. And the equation for the membership function is like this. That's a general equation. Okay, that fuzzy rules. We make decisions based on fuzzy rules.
So K is 1.
Pardon me?
For trapezoids, K is 1.
Trapezoid, which K? This K?
Yeah.
K, we
We
have
have changed the shape of the fuzzy region.
Yeah. We changed the shape. So this is just a general. This is a general equation applies to all the fuzzy functions, and K is not a power. I'm sorry. I should probably put
okay.
a sub
You
K.
can raise these things to powers and change the shape of the fuzzy membership functions.
It depends on how you define the membership function.
Okay, so you're going to Straight track is what.
Yeah, we just do the simple way.
Okay.
Because we feel that's sufficient,
Yeah.
and it fits with the intuitive understanding of the fuzziness of wireless inequality in this case. And the K is not power. You can understand it as a sub K instead of a to the K. Okay. And so basically, different functions have different K. Different AK, BK, CK, DK. Okay. And those are the parameters we need to figure out later on through the learning process. We use the learning process to train those numbers. So the fuzzy rule, basically, each fuzzy rule decides the fuzzy output based on the input. It's an if-then sentence, if-then sentence. And a set of fuzzy rule defined for each rule. Each fuzzy rule reacts to a specific wireless link quality level with each neighbor. Okay, and all the rules for all the wireless link quality levels for all the neighbors are combined together to decide the response a robot should make relative to all the neighbors. And this is flexible to the number of neighbors. Now, if we have more neighbors, we just add the whole block of 5 fuzzy rules to that neighbor, and that's it. Okay, so the definition of fuzzy rules is pretty simple. The strategy is very straightforward, very intuitive. So if let's say a robot has a neighbor which give very strong wireless link quality, then it's above the desired level, then the robot should, how to do that? Just step away. Move a little bit away from that neighbor. Okay. And on the contrary, then the robot should move closer to a neighbor with a relatively weak wireless link quality in order to approach and maintain the desired level of wireless link quality. Okay. So basically, the way we constructed the rule is at different level of wireless link quality, a robot should move towards or move away from a neighbor with a certain step mass. For example, if the link quality is at the losing level, the robot should move a big step towards the neighbor. If the link quality is at a strong level, the robot should step a little bit away from that neighbor. Okay? And if the robot has multiple neighbors, then all these 5 rules should apply to every neighbor.
Is SL a speed? Is that a...
Good question. That's a speed.
Okay.
That's basically a speed.
So they may be negative.
Yeah, that can be negative.
If
Yeah,
it's
can be
too
negative.
strong, right?
Yeah, if it's too strong, can be negative.
Okay, SL4 would be negative.
Yeah, 4, 5, all be negative.
Okay.
How frequently does it go through this computation?
How frequent? Right now in our experiment, the update rate is at like 0.2 seconds.
Pretty fast.
Yeah.
So
Five
it's
times.
continuous from our human
Yeah.
perception, right?
Yeah.
Yeah.
Well, it depends. Right now we're kind of cautious. This is an ongoing research, I would say. Right now we are cautious. We give a higher update frequency. We are picturing that probably we can relax it a little bit because the robot needs to do other things, and in many environments like this, it's pretty stable. It's not, well, I would say the environment is pretty stable. I'm not saying the signal is the signal is still fluctuating, but as long as we stay in a wide enough desired wireless link quality range, we are good. Yeah, but you will see in this work, we kind of go to the extreme. We try to hit the spot, just the value, one specific desired value of wireless link quality. It's a little bit crazy. The result is pretty good. There is some fluctuation, but in general, it's pretty good. That gives us some confidence for more relaxing scenario.
So any single time step, it seems like more than one of these if rules should fire, right? Because each robot is in 2 fuzzy sets, because they're overlapping, or not?
Each robot Well,
Partially belongs
Yes, that's
to
right.
this.
So you have to weight
Yeah.
two speeds.
So yeah, that's a good
The
question.
way the two speeds
You weigh the two
according to
speeds.
membership.
Yes. So that's basically that's the fuzziness. That's the fuzziness. So if let's say you have assessed the wireless link quality, if that wireless link quality belong to this level, the robot should move like this. If that link quality belong to a different level, the robot should move at a different way. Then the final decision, how the robot should move, is a combination of the outcome of all these fuzzy rules. So we have to comprehensively adapt it to all the available situations.
Not only that, you have multiple nearest neighbors.
Well, that's
So
what
you
I'm
have now
saying.
competing
Yeah.
desires to move in this direction to get closer to him, and maybe in this direction to get further from the other guy, so you add the vectors.
Yeah.
You add the
It's
vectors.
fuzzy.
Yes.
Yeah.
So it's a vector addition. Actually, it's a weighted average.
Yeah.
It's a weighted average of all the decisions. Right.
It would
So
make
this
me want to just
this
stay
is
still.
exactly the control structure.
Ah, there
Yeah. So you can see it has several blocks. Right. This is a big fuzzy process. Several blocks. Each block take care of one neighbor. Each block take care of one neighbor. Inside each block, we have 5 fuzzy rules. Take care of all the 5 different wireless link quality level. Okay. And the process, the fuzzy inference process is like this. We take a simple process. The first step is called a fuzzifying input. So we have a measured wireless link quality in real time. Then input to the membership function of the 5 fuzzy rules, 5 fuzzy sets. We get the membership degree, membership value for them. Okay. And the second step is to calculate the so-called firing strength of the rules. Firing strength is just the weight of the rules. Okay. And in our case, it's very simple. The firing strength for each rule is equal to the membership value. That's it. Okay. That's it. And step 3 is called implicating consequence of rules. So for each rule, we define a consequence. Yeah, that's how this robot should move relative to this specific level of wireless link quality. Okay, relative to the neighbor. Okay, and last step, aggregating the consequence. So how the robot should move at the end relative to all the neighbors. It's an aggregation of all the outcomes of all the fuzzy rules for all the neighbors. And that is a weighted average of all those decisions. In this way, we basically take care of all the neighbors.
It's a vector addition of weighted average.
Yes.
Can I ask what WQL means? I know I don't have the right to ask.
W.
Go up,
Wait.
see that your first sentence?
Oh, yeah. This one?
No,
Sense
Probability.
WQL. They sense the WQL.
Oh, W. Wireless link quality. Yeah,
Oh, I'm sorry.
wireless link quality.
Which is what you're using.
Yeah. So basically, you see a neighbor send you a signal.
Yeah.
So from that signal, you can judge the wireless link quality. Okay. Well, that's the control process behind the approach, but the controller structure follows the fuzzy neural network. Controller structure follows the fuzzy neural network. Basically, we just formulate. We formulate, we present, or we structure that fuzzy inference process in this way. So this is a diagram of a fuzzy neural network we use. It has 2 parts. The lower part is called an antecedent network. It's corresponding to the first half of the fuzzy inference process. The upper part is called the consequent network. It corresponds to the second half of the fuzzy inference. In this antecedent network, we have 2 layers. The first layer calculates the membership value of a sensed wireless link quality with respect to all the wireless link quality level. Okay. Then the second layer calculates the normalized file strength for each fuzzy rule. right? Then in the consequent network, we also have two layers. The first layer gives you the consequence of each fuzzy rule. That's how the robot should move relative to a specific level of wireless link quality. Then the second layer, that's the aggregation of all the consequent. So give you the motion decision relative to one neighbor. Give you the motion decision relative to one neighbor. Actually, the motion decision for all the neighbor will be another aggregation of the outcome of this fuzzy neural network. Okay. So that's the structure of control. Well, so we have this fuzzy neural network structure. It contains a lot of parameters related to the fuzzy inference process. Those parameters need to be trained, need to be tuned in order to fit with the in situ wireless communication condition. Have to work with the real environment. So what's the best way? We let the controller to learn in the real environment. So we use a reinforcement learning method to train the controller. In general, reinforcement learning learns to map situations to actions through continuous interaction with the environment in order to maximize some kind of rewards for the actions. Specifically speaking, in our case, reinforcement learning process train our fuzzy neural network controller to make an appropriate response to the sensed wireless link quality in order to approach and maintain the desired level of wireless link quality with neighbors. Okay, so that's the general picture of reinforcement learning. Then, parameters to be tuned, as I mentioned before, just the parameters for the fuzzy control process, including the parameters of the membership functions. You see those A, B, C, D, AK, BK, CK, DK, and also parameters for the fuzzy rules, like the step length, the consequent parameters. So all these parameters will be trained, learned from the interaction with the real environment. How to do that? So the learning process, at this moment, we just do a simple way. So we let a moving robot react to the wireless link quality with a fixed neighbor. So we just, for the training, at this moment, we only deal with homogeneous system. We'll think of non-homogeneous later. For a homogeneous system, we assume all the robots have the same mobility, same communication capability. So pretty much, or at least close with a tolerable tolerance. Okay. Then in this case, if we train one robot, we are done. Okay, the controller can be applied to all the robots. So we let one robot react to a fixed neighbor. So at the beginning, this fuzzy neural network controller just randomly initialize all the parameters, randomly. Okay. Then the initial position of the robot is also randomly picked, just within the communication range of the neighbor. So as long as there is a communication, can be done. That's it. Then at each time t, the fuzzy neural network will update the parameter first to perturb, just adjust the parameter a little bit. And then the controller will decide the next motion for the robot. Okay, according to the sensed wireless link quality.
So MS is the width of the fuzzy set, and SL is the
SL is the step length of the robot. So if I send, so at this level of WLK, I make this step.
What's MF?
What happened after? After that, we will get, as a consequence of this action, we will get a numerical reward. We get a numerical reward which checks that if the signal quality has become closer to the desired level.
What is MF? The MF quantity?
Oh, that's a basically the membership function parameters.
So those are, okay, that's what I was asking, it's the membership function.
Yeah, that's for the membership function, and SL is for the fuzzy rule.
And SL is step length
That's step
on
length.
the fuzzy,
On the fuzzy rule.
on the fuzzy rule.
Yeah, on the fuzzy
Okay.
rules. Yeah. So we have five different step lengths applied to those five different fuzzy rules. And we have 5 sets of parameters for the 5 different membership functions. So we train those many parameters.
So the number of parameters is 10 plus or minus this one or two, something like that.
Over here, we probably have 20. Over here, we have 5. So 25. That all. 20, 25. That.
And that's per robot and per team, because once you train one
Per robot. That's basically. Yeah. Same thing. In this case, it's a homogeneous team. So yeah, that's for every robot basically.
You better catch your computer. Look on
Oh,
your screen.
Starting.
Sometimes I click the 4 hours. I click the restart now.
But
Yes.
one of the desired signal strength is fixed though, throughout.
Yeah.
You don't let that one vary.
It's a range,
No,
right?
that one we don't.
That one,
we don't
that one
have.
doesn't vary, but the others can.
Yeah, I like it.
The other 4.
Yeah, I like
Okay,
it.
the other 4.
That value actually, it depends on application.
Yeah.
Yeah, so.
Okay, so that one's fixed.
Yeah, that one is
There's
fixed.
one less parameter on the left
Yeah.
of the MS, right?
Which one?
The MF value.
MF?
Yeah. What does MF stand for?
MF, that stands for the parameters of membership functions.
Yes.
All the parameters of all the membership
A's and
functions.
B's.
So this is not a very strict mathematical expression over here.
Okay.
So it's just means that over here we update all the parameters of all the membership functions. And over here we update all the parameters for all the fuzzy rules.
Oh.
So we are making a little, not an update yet, but make a little adjustment. Make a little change. Then based on the changed parameter, make a decision.
Okay.
Yeah, on how the robot should move. Yeah, so after the robot make the movement, then there is a reward value which shows if the signal quality gets closer to the desired level. If yes, keep the update. If not, don't update. Right, so that's a reasonable learning attitude, right? Yeah. Then this process will repeat at a sequence of times. Time 1, 2, 3, 4. So repeat. Then at the end, the controller can find a set of parameters for the membership functions and step lengths that can produce actions leads towards the desired wireless link quality. So that's the reinforcement learning process. Then we assessed, we verified our approach in both simulations and experiments. Both simulations and experiments. Sorry. In simulation, we simulate signal propagation condition in different environment using a popular model. That's the log distance path loss model, probabilistic. So it's basically like this. Like this D is the distance between the transmitter, receiver. V0 is the reference distance. M is called PM is the path loss. M is the path loss exponent. That means how fast the signal power gets lost. Okay, and this X sigma, it's a Gaussian variable. It's a mean, zero mean. Sigma standard deviation shows the uncertainty of the signal propagation, basically the fluctuation of the signal propagation, reflecting the attenuation caused by fading. We tried many different environments. Listed over here, the 6 different environments. Then for the wireless link quality, we normalize all the RSSI value and put that into the range of 0 to 1 for all the simulation. So it's easier to manage the data, present the data. And we set a specific desired RSSI value at 0.22. It's a normalized. Okay, and I try to approach that. As I said, it's a little bit too strict. It's impossible to get exactly that number, but close, close. So the learning process. We use reinforcement learning to train our faulty neural network controller, and I'm going to show a little video clip of those learning curves. Yeah, in this picture over here, you will see that a robot move relative to a fixed neighbor. Okay, and in this picture, you will see the evolution of inner robot RSSI value and distance. In here, you will see the evolution of membership function parameters, and in here, you will see the evolution of faulty rule parameters. In general, you will see all kinds of convergence. In general, you can see all kinds of convergence. So over here, the inter-robot RSSI value, let me see, it's over here. This is inter-robot RSSI value. And this is the desired value 0. This is 0.2. Oh, yeah. This is 0.22. This is 0.22. You see, it's pretty close. It's quite reasonable, considering the randomness. Okay. And these two pictures are quite important. That shows a clear convergence trend of all the parameters. Yeah. If the parameters are converged, that means what? Learning process works. Right. Okay. Then we use the trained controller to control the deployment of the robots. So basically, we deploy a team of 50 robots into a different environment we simulated, use the controller. And this is a very typical resulting configuration of a multi-robot system. Each little circle is a little robot, and these links are not real links. These are just topological link made by Brownian triangulation. Shows the topological relationship and actually shows the neighborhood relationship among these robots. And in general, simulation shows our method is capable of forming effective network coverage under different level of uncertainty in signal propagation and different path loss exponents, because really we tried in different environments. Okay, some more detailed results are presented over here. These are the control results. So use the trained controller. So each curve, we have a bunch of curves here. Each curve shows the evolution of inter-robot RSSI value in a specific environment in this throughout the deployment process. Again, 0.22 is the desired value. You can see in every plot, in general, this inter-robot RSSI value converge towards that desired value, But you can see this fluctuation, a very clear fluctuation. The reason for that is because our controller just reactively responded to the randomness of wireless link quality. Because wireless link quality fluctuates. Therefore, the response of the controller also fluctuates. So that's the reason for the fluctuation. But you can see for different environment, the level of fluctuation is different. On the left-hand side, we fix the path loss exponent. We change the uncertainty level of the signal propagation. You can see as the uncertainty level increase, the fluctuation increase. That's easy to understand. Okay. And on the right-hand side, we fix the uncertainty of signal propagation, but change the path loss exponent. As you can see, when the path loss exponent increase, the fluctuation decrease. The reason for that is energy. Because the fluctuation energy decreased. Path loss exponent is the ratio of how fast the energy decreases. So that's very reasonable. So this is a very reasonable result. Yeah, a little video clip for the simulated deployment process. Left-hand side, the evolution of the multi-robot coverage. Right-hand side, the evolution of the inter-robot RSSI value. Again, convergence. Convergence means, well, good. Okay. Experiment. We have to do a little experiment. At this moment, the experiment is pretty preliminary. I have to say, pretty preliminary. We are going to do more complicated experiment. So some preliminary experiments have been done on a physical multi-robot system. This system consists of 4 Pioneer robots and 3 Amiga robots. Onboard, we use an onboard laptop as the main controller. Okay. Then the wireless module, we use Zigbee. We use Zigbee to do the wireless communication. Then for the robot localization, landmarks, stick to the ceiling, little circles, all these things. Then on the top of each robot, we have a camera. So we use this visual landmarks and the camera combination to the self-localization of the robot. The good thing is that we don't need external machines and sensors, expensive system to figure out the position of the robot. So everything is on board. Well, experiments, you may see these experiments are really trivial, but that somehow means something under the limited facility we have. Okay. So this is experiment 1, and this is the initial configuration of those 7 robots. We wish to have like 100 robots to do that. Yeah, may gets closer, but may gets closer. So initial configuration. Then this is the final configuration of the system after 30 seconds. So this is pretty much a process to spread out. Initially, those links are only good. They are probably at the crowding level. Then after that, spread out. Yeah, it's actually the result is pretty surprising to me. I thought that the actual wireless link quality should fluctuate more, but the shape is quite symmetric. Quite symmetric.
Do they ever all rotate together?
They move together. They move.
Okay, so the whole hexagon moves around a little bit?
Well, no.
Does it all stay fixed?
That's another.
They could all turn together or move around together.
Yeah. That's another problem.
That's
that's another problem. That's the formation control.
Yeah.
Formation control. So hopefully 1 year later, if I get chance.
Next year.
Have you thought about using Raspberry Pis? Mounted on some little robot? You know the Raspberry Pi? It's a Unix machine.
Yeah.
It's about the size of a cell phone.
Well, the thing is, I'm pretty bad on Unix machine and Mac. So I'm just, I know Windows is stupid.
I see.
And a lot of bugs.
I'm just saying these would be much smaller, perhaps.
Yeah, I believe so. This laptop, we want to do a lot of control on that.
Yeah.
Not only for just one specific task, we want to do also image processing and
Yeah.
also other sensors.
Yeah.
So a laptop, a computer, a real computer can be more powerful,
Right.
more powerful, more useful. And well, again, under the limited budget, I just want to get one computer and that's it. Yeah, that's it. So this is another experiment, just slightly different. Just slightly different. The initial configuration is different. But again, after 30 seconds, we get similar deployment. So this means something. This really means the wireless link quality in this environment is something learnable. Then after that becomes
It would be really interesting to see this with more robots, right? I mean, that would be really cool.
yeah. Well, probably in the near future, I will get some more cheap robots that make a bigger team. At this moment, I actually have 10 robots. I have 10 robots. I probably spend a few $1,000s to buy 10 more like Roomba robots.
Yeah.
I create platforms. Those are not that expensive. Probably 10 robots cost only like $2,000, $3,000. Okay, some video. I tried to play the video on the slides, but it didn't work. So let's see this. So you see these robots, they keep adjusting their position, their distances. Actually, if the environment is stable, as for wireless communication, then the link quality will be proportional to the, well, may not be, I shouldn't say proportional, but somehow highly related to the distance. So in a totally stable environment, the final configuration should be symmetric, perfectly symmetric, as for the distance. Okay. Another one is pretty much similar, just with a slightly different initial configuration. Then you can see, initially there was one robot. This robot distances are very close, so this robot moved very fast, jump out like. So the robot adjust, and at this moment it just maintain.
Who's seen that as a picture?
Oh, that's my student. That's my student. So that's just the maintenance. Almost there. Okay, summary results. So these are results from the real experiment. Okay, so on the left-hand side, we have the curve showing the evolution of the inter-robot ISSI value with experiment 1. This shows the evolution of ISSI with experiment 2. Again, the desired value in the experiment, we set the whole range at from 0 to 10, and the desired value is 2.2. Is 0.22. 2.2. That's the desired value. You can see with our control approach, the average ISSI value among the robots converge to the range of desired ISSI with some very realistic fluctuation. Okay, but the general trend is very good convergence. So, come to a conclusion. Today I just talked about an ongoing work of a distributed fuzzy neural network control approach, which is used to deploy a multi-robot system to form and maintain desired wireless communication connectivity. The effectiveness of the proposed approach is somewhat verified, quite substantially verified by simulation and somewhat verified by the experiment. Okay, but this somewhat means we have to do further work. So we have to do a lot of experimental research to try the approach in different environmental settings. That's very important. As I mentioned before, actually John asked that question at the very beginning of the talk. We want to combine this communication maintenance controller with a more general control framework to conduct more complicated tasks while maintaining stable communication connections. This is quite complicated. Not only just motion control. We have a general motion control based on dynamics, which has more mechanical engineering flavor. But I think this problem may go beyond that, go beyond the motion control. May involve a task allocation, global-wide coordination. Then also we need to deal with non-homogeneous multi-robot systems consisting of different robots with different mobility and communication capability. Then at the end, I think, well, clearly, right? At this moment, I only work on mobility control. John is only working on wireless communication. So how about combine those things together? Then I bet the communication, maintenance like this will be more efficient. I believe. But I think there's a lot of issue how to combine those things. So we have to think through it.
Do you have some students that are capable of working on this?
Electrical engineering.
What do you think?
Computer science students to both work on that.
It'd be a neat project, wouldn't it?
Yeah, sure.
Currently I have a computer science student.
Yeah.
Doing the I let him do the communication.
Good, good.
He's writing program. He's pretty good. Well, just at the end, always acknowledgement. Thank for the money. Also thank for the students. The students, some student did a pretty good job. Actually, this guy is he just graduated from his PhD program at SUNY. And that guy did quite a lot for the. He was a computer science guy. He did a lot for the visual landmark and image processing work. So give a little thanks to them.
You had a summer student too. Did they work on this project at all?
I had a good intention to, but.
Okay, all right.
But the student working with me this semester, two students, both from computer science. It seems pretty good. Let's see. I want to give them a little pressure to.
Oh yeah. Sure.
But it seems better than the previous student. Okay, well, thank you very much for coming. And if you have further questions, I'd like to.